Okay, so yesterday there was a question about what caused the rise in CO2 during the Cretaceous. Did anybody do any homework on that? I mentioned flood basalts, but I didn't mention the details because I didn't want to go in that direction. But flood basalts, which are basically slow ooze of magma, like the ones that form the Deccan Plateau, can go on forever. And those are often, they can go on for millions of years, for example. They are often associated with mass extinctions also. So in the Pacific, there is evidence that such a flood basalt happened. It's called a super plume. So you can Google super plume and you will get it, which is about maybe 10 times as large as the Deccan Plateau. That happened from about maybe 250 million years ago to 120 million years ago, which is the most accepted explanation as to what could have belched out so much CO2 that the CO2 rose to almost 1,000 parts per million at that time. There are some other details that I won't go into. For example, the temperature we'll come back to this about climate sensitivity. Right now we are increasing carbon dioxide. The most important thing we are interested in is how sensitive is our climate to increase in CO2. That's called climate sensitivity, and there is evidence that this doesn't remain constant in time anyways, but to the extent that we are worried about climate change over the next 100 years, we don't expect the climate sensitivity to change on such a short time scale. It will change on tectonic or orbital time scale. So the change in temperature at the time doesn't correspond to 3 times the increase in CO2. It's about 2 times the increase of CO2 that we would expect. So we haven't completely understood what changed the climate sensitivity at the time. But we will look at these things when we come to how we project and what it is that we are looking for from models when we want to do these projections. So are there any questions from tectonic timescale climate change? We'll come back to that if there are questions, but then what is causing tectonic movements at all? As we said, the upper mantle is like molasses. It's very plastic. It's a lot of heat, so it is very soft. So just the fact that Earth is rotating and you have gravity from Earth, Moon and Sun. Everybody has been exposed to tides by now, right? Everybody knows a little bit about tides. Why is the lunar tidal force much greater than solar tidal force? Huh? The distance 1 over r cube, right? Or r, whatever, I forgot. R4? 1 over r square is a flux, but tidal force is more like 1 over r to the 3 or 4. So sun is much more massive, but it's much further away. So the solar tidal force is almost 50% less than the lunar tidal force. And then Earth's orbit also experiences gravitational pull from Jupiter and Venus and so on. So if you have a soft material on which you have put blobs of tectonic plates, crusts, then the inertia would make them move if they're not fixed. Okay? So
you would think that because of the Earth's rotation, they would try to be near the equator.
While Earth is tilted, you're imagining Earth is standing like this, right? So remember, Earth itself is already squished because the bulge happened because of the centrifugal force and so on. So that is a more permanent effect that has happened. But beyond that, as somebody already mentioned before, the length of day is changing because of friction and so on, because of tides. So everything is still dynamic. Plus, if you change the orbital parameters, then you're going to change probably the centrifugal force. Length of day is changing, friction. So altogether, it's not a static system, it's a dynamic system, right? So everything is moving on Earth. So we think of tides in the ocean, but there are also atmospheric tides which go pretty high up into the stratosphere. So everything on Earth is a dynamic system.
So the superplane you mentioned is for the Cretaceous hothouse, correct?
This is what potentially the best candidate to have put out so much CO2 into.
Wasn't the Deccan and the Saurashtra volcanics also around the same time, like Cretaceous?
When did the Deccan form?
No, this is probably the Permian Triassic.
So yeah.
And then after that, the Cretaceous tertiary boundary was another one. It's about 5, 6
Of what?
mass extinctions and large increased provinces.
Okay, so let's not. I said there are flood basalts which are associated with mass extinctions. There are 5 mass extinctions, but not every one is explained by a flood basalt.
I think it's well established. But yeah, Sharon.
So somebody else can Google. What's your name?
Chintanza.
Chintan,
sir.
Chintan. Chintan says all mass extinctions are well established to be caused by flood basalts. That's what you're saying?
Something I've read.
Dinosaurs were also caused by flood basalts? How many of you think dinosaur extinction was caused by flood basalt?
Happened to be around the same time, but did not cause it.
Around what time?
The 60 million year mark, like 81 million.
There was a flood basalt around 60 million. I'm not trying. I mean, these are like stories, you can read them. Meteorite strike we talked about already, right? Which is very well known to have caused dinosaur extinction. You heard of that?
I've read both sides of the argument.
You read somewhere flood basalt? You
Several
should.
places where flood basalt. But they argue that the iridium signature is actually in between. In some places, it's in between the flood basalt and strata.
Okay. So send that source to Amit, then he can share with all of us, because that's new to me. I haven't heard that before. And the other events before also are not. There are Indian Deccan Plateau flood basalt. When did it happen?
60 right up to 61.
You're sure?
Yeah.
Okay.
It peaked around 64.5, 65.5.
Where was India at the time?
Just north of equator.
Right? So what is the super plume and Cretaceous we are talking about?
So for India, it was reunion. The one you're mentioning, Pacific, is the one that probably caused the Hawaiian Islands.
Hawaiian Island.
That is much before, not in
No. Don't mix random information. I said this one happened 250 to 120 million years ago. Okay, Jurassic is when the meteorite strike and dinosaur extinction is happened. That's 65 million years ago.
Cretaceous.
Cretaceous is before or after?
After Cretaceous.
After what?
Triassic, Jurassic, Cretaceous.
Okay. So the Cretaceous hot house happened, and that happened after the meteorite strike, whatever.
The meteorite strike happened at the Cretaceous tertiary boundary, which is the end of
That's the extinction boundary. But the hot house happened when?
It actually happened during that time. So it's understood happened before the meteorite strike. Then the meteorite strike happened, and then so the volcanism was well underway when the strike happened.
Right. That's the point I'm trying to make. That this super plume preceded all of that.
Yeah.
So the Cretaceous hot house was already going on. And the big thing about the meteorite strike is the debate about whether it is as soon as a big impact happens, you expect a lot of melting of the top crusts, a lot of dust plume, and then there is also theories that diseases happened that killed the dinosaurs. We don't know exactly, but what you can say pretty well is that, and that kind of a crash would also have caused some increased volcanic activity, right? So everything is happening in a sequence, but I'm only pointing that there is an evidence of a massive superplume under the Pacific that preceded all these. So CO2 would have been higher already before because remember dinosaurs were wandering around in the Arctic. We talked about vegetation, no glaciers, there's a lot of tropical vegetation beyond the Arctic Circle when the dinosaurs were alive. If dinosaurs went extinct at 65 million years ago, before that you already had a hothouse. There was no glacier by then.
Yes, that makes sense because they were cold-blooded reptiles. But I don't think the
No, cold-blooded reptiles don't explain why glaciers were not there.
No, they can survive at such temperatures.
But there were no such
There's
temperatures.
no evidence of that.
We already know that Arctic and Antarctic were very warm. Siberia had mammoths, dinosaurs. We already have vegetation evidence that Arctic had tropical kind of cicads and other vegetations.
The Antarctic as well had.
Sorry?
The Antarctic also had temperate climate.
Yeah, that's what I'm saying. Glaciers were not there. Right? So,
Can you please specify the time?
yeah, so so you mentioned the geologic periods. Name them again.
For the Mesozoic,
Yeah.
Triassic, Jurassic, Cretaceous.
So how old is Triassic?
Triassic is 250, starts at 250.
Okay, so there were dinosaurs at 250.
Towards the end of Triassic, the dinosaurs, as we know it, the larger ones came into being.
Yeah.
Around that time, they were mostly in the African and Indian subcontinents, which was around the equator.
It was warm.
Yeah.
And then?
Then in Cretaceous.
No, don't jump to Cretaceous. In between Jurassic. Where were they during Jurassic?
Again, close by the equator. So the Antarctic portion.
I think let me just open the other. Excuse me. It's called Cretaceous hothouse because the drop in temperature we can see starts around 50 million years ago, right? So we didn't say how far back that hothouse went, right? So if you look at, where is our friend? How do I remove this? Yeah, doesn't matter. So here is 600 million, right? This is 540. So you still have ice here at 280, right? Okay, this jumps, unfortunately, I didn't put all of them. But you can go and see the reconstructions between 280 and 65, okay? You already had glacier free, so here definitely no glaciers, right? So this is already, there is no ice here, there is no glacier here. It is already pretty warm. This is before the meteorite crash and before the dinosaurs disappeared. So reptiles, dinosaurs may be cold temperature species or whatever, but the temperatures were warm enough that you didn't have Arctic ice and Antarctic glaciers. So here, let's go, does this help? So you had already the Permian, Triassic, Jurassic, Cretaceous. You are already warmer than before. Okay, so this is the dinosaur period. Okay, so dinosaurs, which appeared here, appeared during one of the warmest periods. Okay, so the figure that I showed before shows 250, there was still Antarctic glacier. Okay, but the land distribution is such that Arctic is not. So this is there is no Arctic as such defined here yet. So when we say dinosaurs were in the deep tropics, we are talking about basically in a very different land configuration. Okay, that's one thing. The other thing is, was there only cold temperature here or also cold temperature there? You don't have, so you see some glacier here, there are some mountains, etc. So remembering that these are reconstructions, we are already 250 million to 120 million is where the superplume is dated as. Okay, so if it started at 250 and it begins to ooze magma for 100 million years, it's going to start slowly increasing CO2. Okay, So you can see that the initial warming almost disappeared, but it remained warm for a while. So this pulse of warming disappeared because we came out of the Carboniferous, which buried a lot of the organic matter and created near global glaciation, which is called snowball Earth. So you can go and read the very nice books, general language books called Snowball Earth. I'm not introducing that here because this goes into explaining there are about 3 snowball Earth episodes, which means the glaciers came very close to the equator. Then the question is, how did that happen? Can you really have glaciers all the way down to the tropics? If you did, again, how would biology survive? Because if you cover the ocean with glaciers or ice and then land with glaciers, the question is, how does light get into the ocean? How would you maintain life? Those are not very well explained, okay? So that snowball Earth episodes don't add much to it other than mentioning here that every time you had huge evolution of trees and they drew down a lot of carbon, you had the potential to cool it down. Then remember, orbital forcing is happening all the time. It doesn't go away. So it pushes it back. Then you have massive sequestration of carbon during the Carboniferous, so you almost glaciate. Then you come out of it, and then you have had this kind of a super plume which maintained it. And we keep saying Cretaceous hothouse because this was the local maxima we are looking at. We are not going back there. We are mostly interested in trying to see if we reached 1000 ppm at this time and we've been cooling for 50 million years, then what could be the reason for that, right? This is where we invoked Himalayas, but remember Himalayas actually rose around 30 to 35 million years ago, not 50 million years ago, right? So as I said, in paleoclimate, it's about technical difficulty and artistic presentation. So you have to kind of match the story with the evidence you have. So the long story short, dinosaurs dominated this period. And this period, we already saw that this vegetation and animals that appear to have been warm adapted lived in both polar regions 100 million years ago. Okay, that's the main point. You should remember that at that time, it was so warm that the Arctic had no sea ice and Antarctica had no glaciers, because Antarctic reglaciation started only about 30-35 million years ago. Right? So why is that important? Because again, if we want to think about global warming and if we are headed towards removing ice from the Arctic, right? We will come back later on to the human issues of global warming. I will get into a little bit about how human mind works. So if Arctic ice melts, will everybody be unhappy? A lot of countries will be very happy. A lot of countries will be very happy. Already they are fighting for an ice-free Arctic. If Siberia becomes snow-free, Russia will be very happy because they can grow enormous amount of wheat in Siberia, right? You could even have nice beaches far north and so on and so forth. So global warming actually will produce lots of winners and lots of losers. Tropics are most likely to be the biggest losers because we have nothing to gain from global warming. And nothing good can come out of global warming for the tropics. So that's why you look at past climates to see what potentially can happen. Okay, so anyway, the super plume story is the best story we have for explaining where this. So basically, the upper mantle, as I said, is plastic. It's very soft, and when you create a lot of heat, it can melt and produce magma. And wherever the pressure builds up, so Hawaiian Islands was mentioned. Hawaii and Galapagos are kind of hotspots. So usually volcanoes happen not necessarily in the middle of a plate. They tend to happen at where the opening is, but if the pressure is high enough, they can actually come out in the middle of the plate. And if you form a volcanic mountain, and if typically the plate is moving, then that magma source is here, the mountain formed, and then the plate moved. So now the volcanic mountain doesn't have a source anymore. So it can collapse and become just a dead volcanic mountain, like Galapagos, for example. The plate constantly moves. So new volcanic mountains and islands can keep forming and will keep moving. So Hawaii is formed similarly in the middle of a plate. Okay, that's a bit too much geology. I'm not a geologic expert. You can read it up. So let's go to the next time scale. The time scale we are splitting into is a bit artificial in the sense we said tectonic time scale, which obviously is millions to billions of years of time scale. In the global warming calculations we want to make for the next 100, 200, 300 years, we don't expect a big dramatic tectonic change, but these are not, they don't come announced, right? So when the big earthquake happened off of Indonesia in 2004 that caused a huge tsunami, the plate moved by about 30 meters. So, and you can imagine if you move an entire water column suddenly by 30 meters, how much potential energy is going to get released into kinetic energy, which is what caused this massive tsunami. But more importantly, it changed the configuration of Indonesia quite dramatically, right? So those kinds of things may happen. Other than that, everything we know about Himalayas rising, Australia moving, everybody is moving. That is kind of a very slow timescale process. But but we looked at the tectonic processes because they have climate-relevant feedbacks. They generate feedbacks in the climate system that did affect climate. For example, this 50 million year cooling, where Himalaya is potentially playing a role. That's an important feedback to understand how the CO2 glaciers, ice albedo feedback work. This is a much more relevant feedback. Milutin Milankovitch was the first one to mathematically formulate the links between orbital changes and ice ages. But before that, I think there was James Kroll, almost 50, 60 years before him, who had also said orbital changes can cause ice ages and so on. But now, typically, orbital processes we refer to as Milankovitch processes. Milankovitch is the name that got stuck with it. So this you would have seen very early on, somewhere in high school or so. The sun is at one of the centers of this ellipse around which all Earth's solar system planets are going around. So here is Earth, and you have the aphelion and the perihelion and so on, the farthest distance and the closest distance to the sun. And you have the tilt, which is now 23.5, and the orbit takes around, let's say, 365 degrees, which 365 days, which changes by a little bit. And twice in a year, sun is overhead on the equator, which creates the same length of day and night at all latitudes. So you have, those are called equinoxes, equal day and night. So you have a vernal equinox in March, and you have an autumnal equinox in September. When you are far away, or at least boreal winter, where the northern hemisphere is pointing away from the sun, we have winter, whereas the southern hemisphere will have summer. And if you look at the distances, actually it turns out that now the distance of the sun during the summer is a little bit further than during our winter, just by happenstance of the time at which we are looking at it, which means the summer is milder than it should be, and the winter in the southern hemisphere is milder than it should be, and similarly winter is milder here and summer is milder, and so on and so forth. Okay, so this is the basic idea. Then what happens when we say orbital parameters? We will see that at some known time scales, the ellipticity of the orbit changes by about 2%. So it becomes more circular in some times and less or more elliptic at other times. And this tilt of the axis is not fixed. It varies from 22.5 degrees to 24.5 degrees on a given time scale. And the Earth itself precesses. So if you imagine a top you were playing when you were a kid, When it's rotating very fast, it will stay straight, but as it begins to slow down, it begins to wobble. That's called a precession. That's the precession of the axis. But the more important precession is that because of the gravitational pull of the other planets in the solar system, the axis itself, the orbital axis itself, kind of precesses. I'll show an animation in a minute. So all those three changes, the obliquity change, the ellipticity change, and the precession, must be accounted for in terms of whether that will change the distribution of energy or it will change the total amount of energy that's coming in. So if you didn't have a tilt, obviously you wouldn't have seasonality. You would just go around and each latitude would be seeing similar energy throughout the year. But because you have a tilt, you are facing towards the sun in one part of the year and you're facing away from the sun in another part of the year. So if you change the distribution of energy from the pole to pole, you would change the seasonal contrast of the hemispheres, right? This would determine equator to pole temperature gradient. This would determine how much energy you have to move. This would determine where the glaciers would grow and so on and so forth, okay? So that's the basic idea. So those are the basic orbital parameters: obliquity, precession, and ellipticity. So as I said, right now, this is slightly farther away in the summer solstice compared to the winter solstice. And the angle right now is 23.5 or 23 and a half, 23.4, whatever. So we need to just then see how three of them together combine to produce the various timescales. As we have been saying again and again, there are feedbacks in the system. So even if you know exactly at what timescale the orbital parameter is changing, you have to then add that to the feedbacks in the system to see what timescales the system generates given a perturbation. So you are making a perturbation to the forcing by changing an orbital parameter, right? Then internal ice albedo feedbacks begin to happen. Do they necessarily stick to the orbital forcing timescale or do they generate a very different timescale? We'll see that there are very rich spectrum of timescale in the Earth's variability on long time scales, and that is often triggered by the orbital forcing, orbital perturbation, but then internal feedbacks take over. So the simple fundas you already know: wavelength, frequency, and then you have these kind of modulated cycles, right? So if you have orbital obliquity varying on some time scale, and then you have precession or ellipticity varying on another time scale, then potentially you can produce these kind of modulated cycles. Does everybody understand intuitively what this means? Is there somebody who doesn't understand? I'm not going to go into the maths of it, but it's not very difficult. You can look it up or we can do it, right? So the amplitude of one particular orbital parameter can be modulated by another orbital parameter. So obviously you can see that this has a higher frequency than this green line that is sitting on top of it. Okay, so we'll see that in fact one of the parameters has a very long time scale and the two others have much shorter time scales. That's what gives you this modulation of annual cycles. So here we are. Tilt is varying from 22.5 to 24.5, and it has a dominant 41,000 year time scale. And you can see that it's not constant because it's modulated by either ellipticity or precession. Is this clear? So essentially you have the tilt increasing during some time and decreasing during some time. In the current, in any configuration, the orbit works in a way that one hemisphere is facing the sun in its summer. Why does it say winter? Okay, so the other, yeah, so it's facing away from the sun in its winter. And if you change this tilt, if you reduce it or increase it, you will not change the annual amount of energy received because you are not changing the distance, right? But you are going to change the distribution or the seasonal contrast of the two hemispheres. If you increase it, for example, this is going to be tilted more towards the sun in its summer, this is going to be tilted away from the sun, more distant, more away from the sun during its winter, and the other way here. So the amount of energy being received is the same, but you are changing the seasonal contrast. The other thing to remember is we are always going to worry about radiation value, not necessarily over the whole sphere, but something like 65 north in the summer. This is something you intuitively should understand, but why would you want to look at change in summer radiation at 65 north or so? Why would you first want to look at summer radiation change? This goes back to when snowfall starts and when glacier melt starts or glacier accumulation starts, right? If, for example, you are worried about ice albedo feedback and you have some ice, let's say, or snowfall already on the ground, 65 north summer is kind of coming towards the end of the melt season. Anything that survives to the end of the summer is going to survive through the winter, which means you are probably going to accumulate more during the winter. So now, when you talk about Arctic ice, they always say September ice disappeared, summer ice disappeared. That's bad news because refreezing during the winter will be hard if it's completely disappeared. But if it's already there, then the ice albedo feedback can pick up in the winter months, right? So given all the distribution change, seasonality, and the whole sphere, you can focus on one particular point which is most critical for perturbing the ice albedo feedback. Is it clear?
What's this one particular point?
We'll see again and again that 65 north is kind of the critical latitude at which the radiation change has the potential to trigger ice albedo feedbacks in the growing sense or in the melting sense, right? If you increase radiation at 65 north because of orbital change, and that begins the melt of glaciers or snow, then that would reduce the albedo, increase energy absorption, and continue the ice albedo feedback in the direction of rapidly melting glaciers. Or if you reduce the energy being received at 65 north in the summer, then you would begin to cool the temperatures, accumulate more snow and ice, increase albedo, and you would continue to grow the glacier and have a positive feedback in that direction for ice albedo feedback. Okay? I'm just throwing it in now because we'll see again and again that we are looking at, but you already heard that when we talk about Arctic, we're always talking about summer ice. We never say winter Arctic ice, right? We say summer Arctic ice disappeared. That's one of the reasons why we do that. So Earth's eccentricity change is remarkably small. It's a very, very small percentage change in circularity, and it has these multiple timescales with two dominant timescales. It has a 100,000 year timescale and about 400,000 year timescale. So immediately you should remember when the time series we have been looking at of the glacier from Vostok, where we talked about committed warming, CO2 change, temperature change, methane change, and so on, that had about 100,000 year time scale. Okay? It'll turn out that obviously this is different because when you change the ellipticity, you are moving away from the sun or closer to the sun, right? So you are changing the total amount of energy being received because of ellipticity change. But it turns out that that energy change is very small. Okay, it's only when eccentricity or ellipticity combines with precession that you will get much larger impact or perturbation to the energy balance of the Earth. So eccentricity by itself doesn't operate. But you also see now why we looked at modulated amplitude cycles, because this is a very long time scale compared to this. And we'll see that precession is even a shorter time scale. So this can modulate this one. So you can see that already this is a modulated cycle. Does that make sense? Yes.
What causes these two different
Everything about Earth's orbit change is related to gravitational pull from other planets in the solar system and beyond, but mostly it's a net effect of everybody is rotating, everybody is coming closer, farther, and everybody is feeling each other's gravity. So that basically pulls things in different ways, on different time scales.
So in those terms, could you understand why there are two different time scales?
Yes, so Milankovitch mathematically put a formula to all these, including everything, and he's the one who came up with these time scales. So it's not made up. It's hard to observe. This couldn't have come from observation, right? So it is something that mathematically formulated by Milutin Milankovitch. And precession, as I said, precession is basically like a top. This can spin around like this. It's about 26,000 year time scale. And we will see that the orbit itself keeps wobbling. So it keeps moving. So it's like this. So this is the precession of the equinoxes. This is referred to as precession of the equinoxes. So the gravitational pull from other planets is actually spinning the entire orbit of the Earth around the Sun, which means when the Sun is on the equator or when is the winter solstice and summer solstice is happening, depends, the distance from the Sun at that time is very different depending on the phase of the precession. Okay, so that's also called a shift of the perihelion or the precession of the equinoxes and so on. These are the various terminologies used. So it's called also apsidal precession or precession of the ellipse, many names. So you can see that in the current climate or the current configuration, we have equinoxes on this side and solstices here. You can very precisely predict that in about 5,750 years, you are going to have the solstices happening when the Earth is here, and the equinoxes are going to happen when the Earth is on opposite sides here. Which means what? Basically, unless we want to keep changing the calendar, we have to keep moving the calendar. So your great-great-great-grandchildren will slowly see the change in the calendar, right? 11,500 years from now, you will have another configuration and so on and so forth. So this kind of orbital change is constantly happening. So on tectonic timescales, we didn't talk about the orbital changes at all because we were mostly focused on moving of the continents, Drake Passage opening, Isthmus of Panama closing, Himalayas, etc. But as they are happening, all these orbital parameters are also happening. But when we come to the modern timescales, we will see that this has had, all these orbital parameters have had serious consequences. So the water cycles that have created extinctions of civilizations, for example, Mohenjo-daro, Harappa, or the African civilizations, they were all precession-forced monsoonal changes. So there is a very strong precessional signal in the monsoon, for example. John Kutzbach was the first one to find this out in the 1980s, but now it's very clear that from observations and modeling, precession has a very strong impact on the monsoon cycle. So once the monsoon got established 10 million years ago, it's been having this precessional cycle. So around 9,000 years ago, there was a monsoon maximum, which is clearly seen in African civilizations and greening of Africa. And then around 2,500 years ago, or whenever the Mohenjo-daro Harappa disappeared, there was a severe drop in the monsoon. Yes.
The last slide for eccentricity, there were two time
which one is there? There's nothing like standard. It's a question of when the modulation happens. You can see that this is showing two modulations, this one and this one, right? So you can see that this is modulated. There's a smaller one here, a larger one here. This is the amplitude of the change, right? So the combination of eccentricity and precession, it turns out that it picks 100,000 years in the record we have. But this is a sampling issue, right? As you go back in time, you don't have very high resolution information. So if you had 4 billions of high resolution information, then you would probably find this time scale as well. Okay, so it's a matter of sampling. Because the we are casually saying that there are evidences from the past from geochemistry and so on. But what is the time resolution of those proxies? If you remember the time series we saw going from the 50 million years ago to present, we'll see that again at some point. The previous data was very coarse. It was a big, smooth time series. It didn't resolve even 100,000 years. But when you come to last few million years, you'll begin to see 41,000 year time scale and 100,000 year time scale. That doesn't mean that that's the standard. It just means that we don't have data long enough to catch the other time scale, right? That's always an issue. For example, if you are relying on, let's say, coccolithophores or foraminifera diatoms in the ocean to look at their calcium carbonate shells, then where are these phytoplankton being produced? In a region where a lot of biological productivity happens, right? Where does a lot of biological productivity happen? We haven't learned it yet, but it's in places where there is upwelling. And upwelling doesn't happen everywhere. So where there is upwelling, you will get a lot of information. Where there is no upwelling, you will get very little information. Right? That's how you have to think about it. Okay? So that is the apsidal precession or precession of the ellipse or the precession of the equinoxes. And all these are easily predicted using the mathematical formulas that our friend Milankovitch put down. So this is just showing extreme solstice positions again. So now you have June solstice and December solstice, and you can completely flip it and have December solstice and June solstice exactly in the opposite. So here June is pointing to the sun, here June is pointing to the sun. So, but it depends, you flipped, so here it's happening at aphelion, whereas here it's happening at perihelion, right? So all these parameters are changing. And as I said, it's not just the amount of energy that's being received, but where and at what time that critically matters to trigger the feedbacks. Ultimately, it comes down to saying how the energy change because of the orbital parameters is going to trigger internal feedbacks. Right? That's always a critical question. Will it start to build the glaciers or will it start to melt the glaciers or change the monsoons and so on and so forth? So this is essentially showing the angular motion of the precession, which is happening at 23,000 years, and eccentricity at 100,000 years, and now you have eccentricity modulated precession. Okay? So as I said, the precession change is not very big. The radiation changes that happen because of the change are also not very big, but because eccentricity can modulate precession, you can see that the precession cycle is remarkably modulated by eccentricity. Precession is highly modulated by eccentricity, which means you are taking these two very different time scales and producing potentially a very different time scale here. So depending on whether this orbital change happens or this change happens, you might get a very different signal in the ice ages or the monsoons and so on and so forth. Is it clear? It's very simple actually, but the interesting part is to see, you have a question? Interesting part is to see what kind of precession signals, obliquity signals, or eccentricity signals are there in the records that we have. You've already seen one where we went from 41,000 years to 100,000 year timescales. So now you can see the question of which is a dominant time scale. If you go long enough in time, you will see that there are times when 23,000 year time scale is kind of dominating. And if you look at the longer envelope, you also have the 400,000 year time scale. And of course, you have the 100,000 year time scale. So the longer the record you have from observations, the more likely that you are going to get all time scales manifested in the record you have. The additional complication you have to add to that is that these things are going to depend on the latitude. Who dominates where is going to depend on the latitude. So this is going now from the current time scale to about 300,000 year time scale. The last ice age was this one, and then the previous ice age was over there. So this is going from 80 north to 80 south. So you can see that the June insolation changes here are dominated by the precession cycle in the northern hemisphere, whereas in the southern hemisphere, it's dominated by the obliquity or the tilt cycle. Okay, so this is obviously a 41,000 year time scale, and this is more like a 23,000 year time scale. This is modulated by eccentricity. This is not so modulated by eccentricity. Okay, and the same way here, you are saying the December, so this is the June changes, these are the December changes. You can see that here in December, it's just a flip of it. So you have obliquity changes dominating and then precession dominating. Okay, so there are three parameters. One is modulated heavily by eccentricity, and then it depends on which year of the, which month of the year you are looking at and which latitude you are looking at, right? So this is what makes things so complicated in terms of trying to interpret the past changes that you are observing. And we'll see that despite this, there are many things that are still completely unexplained. So you will get time scales of observations which are very clearly recorded in geochemical tracers and so on, but we don't have a very clear explanation of what processes could have extracted those timescales from the given orbital forcing and so on. So you have these basically provide the initial trigger, and then internal feedbacks create a new timescale out of it. So that becomes very difficult. So you also have to understand in terms of the phasing of the insolation maxima and minima. So you have obliquity changes where you get maximum and minimum and maximum. So it's kind of synchronized changes in insolation because of obliquity changes. But if you think about precession, you are basically moving the entire orbit, so you are changing the equinoxes and the solstices. So in that case, you are having out of phase. So if this is a summer and you are having a minimum, if it's a winter and you are having a minimum, then you are essentially increasing the contrast and or decreasing the contrast depending on which time of the orbit this happens. So you can have in-phase hemispheric changes or out-of-phase hemispheric changes in the orbital forcing. These are the details that you don't necessarily have to remember, because you can easily go to the textbook and just look it up. But what you want to remember is the physics that then happens because of these perturbations.
Manifests into insulation variation.
Which manifests into? Yeah, so these.
The phasing.
This phasing is going to, well, basically it's going to determine the seasonal contrast. Okay, so remember we have to go back to our circulation. So The question is, we looked at Hadley cell, we looked at thermohaline circulation and so on. Eventually you have to understand whether changes happen synchronously on both hemispheres or they are asynchronous. Okay? Then if they are synchronous, is it happening, the synchronization is happening through the atmosphere or through the ocean? If it is not synchronous, then why it is not communicated from one hemisphere to the other? Okay, these are just perturbations to the forcing and initiation of feedbacks. You have to then go back and put that in the context of all the processes that you understood so well by now. That's where all the tricks are, how to explain it in terms of the physics of the climate and the feedbacks in the system. That's the more difficult part. Okay, this is easy, this is easily calculated and so on. So the question is, if you, for example, now you have Antarctic glaciation and Arctic ice, right? So because of global warming, let's say you remove Arctic ice, then how does it change the energy balance? How does it change equator to pole temperature gradient? How does it affect the thermohaline circulation? Then how will it begin to affect the Antarctic glacier because you changed the Arctic? That's one thing. Then on what time scale that happens, right? This is where humans are perturbing the system. But when you look at this in phase, out of phase kind of forcing, in the past, what has happened, right? The question of why Antarctic glaciation started 34 million years ago, for example. We said it has something to do with Drake Passage, but Drake Passage actually opened 20 to 25 million years ago, and Antarctic glaciation actually started 30 to 35 million years ago. So all these are still very unexplained events, okay? This is just repeating now the cycle of amplitudes, 100,000, 41,000, 23,000. And if you combine them, you're going to have this 100,000 plus 23,000 year cycle, 41 plus 23, 100 plus 41 plus 23. So you can now see that the system has many combinations of forcings that can happen, which means it doesn't mean that the data record will show this cycle, and this cycle. It shows some combination of all those things based on which is forcing. The other additional complication is that if you look at over millions, hundreds of millions of year time scales, the precession itself is changing and the obliquity itself is changing in terms of the time scales at which they change. This goes back to the question of why length of day itself is changing. Who was saying there was 18-year day before? Huh? Who said that? She's absent. She dropped out. I think number is declining day by day. So, did anybody Google it? Somebody can Google it and see if there was actually an 18-year day at some time in the past. Anyway, so the precession cycle was, if you go back in the past, about 400 million years ago, it was at 20,000 years. Now, because of all the changes in Earth's orbit and tectonic redistribution of continents and water masses and so on, you have now precession at 23,000 years. Similarly, the obliquity cycle was at 30,000 years in the past, and now it's 41,000 years in the current configuration of planets and Earth's continents. So obviously this also has to be taken into account, but as I said, at these 400 million years ago, we don't have any time series that we can get which can resolve precession very well. Plus there are additional applications even when you look for fossil evidence and so on. Since ocean's crust is constantly reforming, in about 200 million years it has completely reformed. So nothing remains at the bottom of the ocean that is older than about 200 million years. So on land you will find rocks that are obviously billion years old and so on, several billion years old. But if you go to the bottom of the ocean, you will not find anything that's older than about 175 to 200 million years old, because the ocean crust is constantly reforming.
The entire column of the crust is forming, or if we go deeper, we can find some.
Entire column. There is not much column. It's a fairly uniform compressed crust, which is basaltic and has constantly magma comes up, forms a new crust, it spreads, and it ducks under the continental plates. And the only interesting thing there is sometimes that rate is faster, in which case there is not enough time to adjust, so the sea level rises. Sometimes it's much slower and adjustment time is there, so sea level doesn't rise. But there is no gradient within the crust.
So what is at the bottom? It gets mixed with the magma underneath, and
No, it comes up, it basically has to cool down and form a crust. At that point, it's well mixed. Okay.
So the thing which was earlier then, it also mixes with new.
Yeah, as it goes under, it again under pressure it melts, becomes magma again, which supplies the volcanoes and so on. Right? It's a constant cycle. It happens on tens of thousands of years, so it's pretty fast process. So we just add a little bit about Kepler to it, and we say the first law is orbit of each planet is an ellipse with the sun at one focus. We already know that. The second law is that a line joining a planet to the sun sweeps out equal areas in equal times. This turns out to be a very critical one, because only recently people started to apply these, because there are many issues of explaining the orbital changes and how they affect the energy balance. This one turned out to be a fairly crucial one. Third one is not so important. The square of a planet's orbital period is proportional to the cube of its major axis. So we are talking about apsidal precession or precession of the equinoxes and so on. So the idea is that as the planet moves in this orbit around the sun, the planet covers certain distance and it sweeps out equal areas in equal times, right? Which means when it's closer to the sun, it's moving faster. It has to move faster here than here. What does that mean in terms of energy?
You have excess energy for a low time compared to low energy for a long time.
Right? So if you think about summer insolation changes, you think because you are here, you will have more summer energy. That's not necessarily true, because here you are moving faster. Okay? Summer here is less hot, let's say, less severe, but you are staying longer in summer. Which means what matters is the amount of energy you receive during the whole summer, not just what the peak temperature could be. This turned out to be a very critical piece of information which we had not accounted for even 10 years ago. Only Peter Heuber from Harvard started to put this into arguments about 10 years ago. So this is important to remember, because when you are closer to the sun, you might have a more severe summer, but you will get out quickly. So summer will be shorter than if the summer happens when you are here, because summer is less severe, but you are going to stay in the summer season for a longer time. Yeah.
So does the total amount of energy received turn out to be more?
Yeah, so that depends on the total orbit. It's just, you can do the calculation, but what we are worried about, again, as I said, is let's say summer insolation, because that determines the ice albedo feedback, right? So in that sense, we are saying that we cannot just look at maximum insolation in the summer. We have to look at the integrated energy you are receiving during the summer. Okay? So it seems complicated, but actually it's not. It's just that people had kept on looking at maximum insolation based on orbital position.
Also, earlier you were saying that sun is not exactly at one of the focus and it is more
Yeah.
center.
Sun is at one of the.
Yeah, early in one of the first lectures you were saying that sun is not exactly at one of the focus and it's more circular than
The eccentricity changes.
Yes.
In this elliptical orbit, you will be at. What is the question?
No, I mean, if I recall from in your first lecture, you were saying that you expect sun to be at one of the focus, but it's not exactly at one of the focus, and it seems more towards the middle of the two foci.
Is that what I said? I don't remember bringing this up.
Both foci are very close to the center because it's an almost circular.
It's the eccentricity is very small. That is the main thing to remember. But nonetheless, it's elliptic. Even 1% away from circularity is ellipticity. So I don't remember bringing up focus and all that in my first lecture. But go through the PDF and see if I did I say something wrong. I don't remember bringing this up at all.
No, as you were saying that.
Yeah. Okay. So let's then try to understand some of the orbital forcing mechanisms that are manifest in the climate signals. So if you look at the current monsoons, we have the so-called South Asian and East Asian monsoons, which basically covers India, China, Thailand, everything in this region. This is called West African monsoon. This is called South American monsoon, and this is called North American monsoon, but you can see that they are weak monsoons. Everybody knows where the word monsoon came from? What does it mean? Right? Mausam and season. So basically it was related to the changing direction of winds. So the Persians and Arabs at some point figured out that if you want to go to India, go in the summer because winds will push you this way, but if you want to come back, wait till winter. Right? So this is why it was called Mausam or season. But now anywhere where you have a little bit of winds, they start calling it monsoon because Indians didn't trademark it. Right? Just like curcumin and turmeric and all these other things. Every time you find out something, you trademark it. Okay? If you find something about the foci, then immediately you trademark it. So here are the minor monsoons or the weak monsoons. These are so-called major monsoons, strong monsoons. And some people refer to this together as global monsoon. But you can imagine that if the ITCZ is running around going north-south, that ITCZ on land can create like a monsoonal rainfall. And in fact, here it's not called ITCZ anymore. Sulochana Gadgil likes to call it tropical convergence zone because it's not intertropical anymore. It's just converging within the northern tropics and so on and so forth. Even Australia has a little monsoon. So, as I said, John Kutzbach, about 1980s, so almost 40 years ago, was the first one to argue using a model that monsoon must have a very strong precessional signature. This was before the data had clearly shown it. Since then, there's been a lot of data that confirmed that John Kutzbach was basically right, that monsoons have a very strong precessional signature. So what is the orbital forcing of the monsoons? We'll keep coming back to this even when we do the Holocene. Holocene also has a very strong orbital signatures. Okay, so you look at solar radiation. This is the annual mean current radiation. So that is the black line, the modern seasonal cycle. And you can have orbital forcing where it's weaker in the winter and stronger in the summer. So if you go back to our land-ocean contrast, then stronger summer radiation will create potentially stronger summer monsoon. So if you increase the heating of the land, then you will increase the meridional temperature gradient because the land is low heat capacity, warms faster, then you have stronger gradient and you potentially can bring more moisture and so on and so forth. And if you have weaker winter radiation, then also you can cool the land more than the ocean because of heat capacity again, and you can also have a stronger winter monsoon. Okay? Now this is not theoretical anymore. We will see that actually civilizations have been heavily impacted by changing monsoonal rainfalls in the last 10, 12,000 years. Okay? Is this clear? If you really want to get into the details, then you should remember what I said before, that even though we say monsoon is land-ocean contrast, actually when Indian monsoon happens, land actually cools. It is the energy released by condensation, heating, and the monsoon that drives the circulation. But those kinds of details do not change the fact that you probably need the initial land heating to create the pull of the ITCZ to the north. Right? Remember the ITCZ animation? ITCZ goes way north over the Indian subcontinent. That kind of a pull, remembering that ITCZ is the maximum heat region where convergence happens. So you need to pull it first. So March, April, May, when the warming is happening and the winds are changing and the moisture is already being built up, gets very, very humid in some places over India, coastal regions and so on, that still needs the summer radiation. Okay, so radiation is important. So if you put that in the context of June insolation over the last ice age, so the last ice age essentially started about here. So you have the modern insolation shown in this blue line. And let's say there is some kind of so let's say the land heating contrast requires certain threshold. If you have heating and the contrast is not strong enough, then maybe you don't pull the ITCZ north enough, maybe you don't get a monsoon circulation, right? Considering that in the past monsoons have become very, very weak and resulted in civilizations going extinct, then obviously this is not a joke, this is serious. So you have some kind of a threshold. So when you increase the June insolation at 30 north, now we are using, so as I said, for glaciers and so on, snow ice albedo feedback, we use insolation at 65 north. When we're doing monsoon circulation, we are using June insolation at 30 north as a threshold. This simplifies things. So whatever orbital change is happening, if you can estimate radiation change at 30 north, you can probably use it as a threshold, right? So there are times when you cross the threshold and you have a monsoon response, and these are recorded in lake sediments and so on. So if you go to certain lakes, let's say in, what is that country in the north? North of South America, there is a big lake where the runoff happens. There are also coastal sediments off of Africa and India. Essentially what happens, when there is a strong monsoon, vegetation is growing and you have a lot of organic matter that is coming in the rivers. Rivers have a lot of runoff during the strong monsoon year, right? Organic matter, as I said, as soon as it comes into the ocean or the lake, there are bacteria which are going to eat it because it's a hydrocarbon. It's food, right? But it takes them certain time to respond and eat it. If the monsoon is very strong, then you keep dumping a lot of organic matter and that organic matter doesn't get consumed. Okay? So if you take a core, you will have periods where organic matter increases by a lot. There are things like sapropels, which are all the nice buzzwords you can try to remember if you want, so that you can repeat it in the next summer school. And there are lots of organic matter that you can find. So essentially, it's a proxy for the variability in rain. Okay, every time you do this, you go 120,000 years ago and say there was increased monsoon, you have to find an evidence for it. As this is saying, there is a response in lake levels. So how do they do that? Basically, if you have a lake, these are again where so-called uniformitarian principles and so on matter. So you have a lake level and you have certain species of phytoplankton or zooplankton that live in the lakes. What they do is they look at the distribution of the species at the edges and in the middle. Okay? And they say if the lake level rises, then the species will be distributed uniformly. And when the lake level drops too low, then the concentration of the species will increase in the middle. Okay, these are very approximate kind of proxies, but they calibrate them in modern times and so on. Everything is about calibrating your explanations from the past, right? So this is approximately how they would infer monsoon response in lake levels. Yeah.
Is this essentially assuming that the center is shallower than the edges?
No, it is, you don't necessarily need it. You just, as it drops, the production is, so you need lights, nutrients, and so on for production. So as it drops, you're assuming that the center is getting the light and so on. Productivity is going to remain in the center all the time. You don't necessarily need topography. So you just, obviously assumptions, but it works depending on the size of the lake and so on. It approximately works. So, and you are always looking for relative change. You are not looking for absolute change. So you're just looking at change in the concentration of species in the middle versus the other regions.
So how is this threshold value developed or calculated?
So you can see that this doesn't show any real number here. So this depends on which monsoon you are talking about. Okay, so this will be having a very different threshold than this, so these are different and so
Do you
on.
look at it in terms of anomalies or you...
These are anomalies. So there is, I don't know if I want to go in this direction or not, but it is kind of, this is a very qualitative figure. What you are doing is not necessarily saying, is there a threshold and this is going above the threshold, because there is no reason why the threshold should remain the same. Right? If Tibetan plateau has been rising at 1 centimeter per year, then 140,000 years ago it would have been very different. But the point is, they have data for varying lake levels, and they can say which periods the monsoon was stronger and weaker. And they know this very well because the insolation changes can be calculated very well. Then they qualitatively fit where it was above anomalies, basically. Okay, so it is kind of approximate. Nonetheless, you have these monsoons. So here is the West African monsoon. Again, remember the ITCZ is sitting right there. So is it the ITCZ moving, or is it really a monsoon? It is a monsoon to the extent that winds are changing direction. That is now kind of the approximate definition of what a monsoon is. As long as seasonal changes in wind directions happen, you call it monsoon. Okay? So when the southeast trades are strong, there is a strong Ekman divergence, and you have stronger upwelling. So there is more biological production. And when this is strong, typically that means the northeast. So if you remember the ITCZ, you have to get an intuition for these things somehow. Okay, so if the equator is here, ITCZ is to the north, right? So southeasterly trades are coming into the ITCZ, and northeast trade winds are coming into the ITCZ. The general principle that works is if the ITCZ is typically north of the normal position, that means southeasterlies are stronger than normal, which also means the northeast trades are weaker than normal. This is pushing everything north. You're creating a strong upwelling. Why do we worry about this? We're talking about weaker monsoon, but we are worrying about this. Why? This is how you have to start connecting things. You are looking for a weak monsoon signal. You may not find anything here. There are no lakes, it's a desert, or there is forests here, there is Sahel with some transition to drier vegetation and so on. Why do we worry about this?
From the core record, whether there has been a plume or not, which will reflect the upwelling conditions.
Right? If you have upwelling and you have production, that means there is a biological signature. So you can relate the upwelling and biological signature to whether the monsoon was weaker or stronger. Okay? Is it clear? Very simple actually.
It actually does not depend on how much rain a piece of land has received, just how much of it has been.
Just relative. Weaker, stronger.
If I say, suppose in a year, due to the trade winds, so much amount of moisture enters the entrance of continent.
Due to what?
During the monsoon time, a certain amount, X amount of moisture enters the entrance, but there's no actual precipitation for whatever reason. So is that considered a strong monsoon? Because there's no precipitation per se, but the reversal was strong.
I mean, Indian monsoon has become very weak and very strong. Is there ever any year where it didn't rain? It's very hard to happen because this is still, ITCZ is still there. So you are imagining some extreme situation which actually has never happened. You will always get some.
Have a strong monsoon with less length of rainfall, comparatively lower millimeters of rainfall.
Huh?
It will be a weak monsoon then.
Yeah, so that's my question. The weak or strong, these words, are they associated with the amount of rainfall actually received or the magnitude of the reversal and the intensity of the reversal?
Yeah, so the question you're asking is much more about how strong a proxy is this for actual rain.
Yeah.
That is calibrated from modern times. In the modern times, we know that strong southeast trades and strong upwelling here corresponds to weak monsoon rain. This is saying weak monsoon winds, but actually it's weak monsoon rain. Okay, so you are because of this you are worried, but it is now calibrated against everything is calibrated against modern times, right? So here weak southeast trades, ITCZ is preferably to the south. So you have strong northeast trades, but locally it produces heating contrast. Again, remember you need land-ocean contrast. So you have strong monsoon winds. Okay. These arrows and all are drawn randomly. This is Sahara, there is no rain there. But if you go back to 9,000 years, you will see that this region was completely green. Greening of Africa is part of this story, but right now this is all desert. So the idea is when you have ITCZ preferentially north or south, what do you get here? Weak monsoon. So it is relative amount of rain, and it is rain, not just wind. You want to calibrate it against rain, not winds. Okay. Only point I'm trying to make here is that the productivity signature is being extracted from somewhere else. Okay. Again, calibrated for. I can stop here because I have another. Since you raised this question, I want to make another point about what are the potential for misreading strong monsoon over India based on the winds here. It was calibrated, but actually it was calibrated slightly wrongly because it depends on if you have strong winds here, does this cause upwelling here? Does this cause upwelling here? It turns out that This is something you can think about. When we said, when winds blow like this, do we get upwelling here or downwelling here? Why?
Push it to the right.
So to the right? If you drag water like this, Coriolis will push away. But how do you get upwelling or downwelling here? Huh? So if your winds go like this, you will get upwelling here. It's very easy to say there is Ekman divergence here or there is coastal upwelling here. We didn't say what causes upwelling in the open ocean, but you can still use your Coriolis and try to figure it out. So why don't you come back on Monday? Whoever explains open ocean upwelling here, think about it. Use your Coriolis. You're trying to lift water. What should happen? What winds do you need? Okay? See you in 5 minutes for if there are any questions.